So we have a couple topics left when we're talking about reactions. And the two topics we have left is to classify reactions. You remember back in chapter 3, we classified reactions, or we classified matter. We said, oh, this is a heterogeneous mixture, this is a homogeneous mixture. And we did that so that there'd be language people could use to make it easier to talk about things. We wouldn't have to describe it over and over again every time. What's the point of actually all these languages we learn when we take science classes, math classes, or any other class really, is to have a concise way of talking to each other about these things. So one of our topics is types of reactions. Certainly we do a lot of reactions in chemistry, and what we want to be able to do is talk to people and say, oh, I've got an oxidation reduction reaction, or I've got a single replacement reaction, and everybody knows what that means without having to re-describe it all over again. So I'm going to put out all these definitions. We're going to do an example of each one of them, and we'll go from there. So one classification of reactions are what are called combination reactions. And combination reactions are exactly what they sound like. You get two or more two or more substances. Remember, a substance is an element or a compound. Two or more substances combining to make one. An example of that kind of reaction is if you take iron, react with oxygen, you get rust. And so we get 2Fe plus O2 combines to make 2. Actually, that's not rust, but it's a type of rust. So we get 2 ions reacting with oxygen to make iron 2 oxide. And what do we have? We have 2 or more things on the left. And by things, we're actually counting just different types of atoms or elements. We're not counting the coefficients in front. So our 2 things are iron and oxygen. And we're combining them to make one thing, which is iron 2 oxide. And again, we don't look at the coefficient up here. It's not making 2 different things. It's making 2 of the same things. So we call that a combination reaction. Now we can also have the opposite of that. We can have when one thing falls apart into 2 or more things, and we call that a decomposition reaction. There you have one substance forming more than one substance. What's an example of that? Well, the opposite of the reaction we just did. Every combination reaction, if you undo it, is a decomposition reaction. So if I took iron 2 oxide and I heated it up, one way to say about heat is to use a little triangle, that delta triangle up there that says I'm heating it up. I can make some iron and some oxygen gas, and that's a decomposition reaction. One thing, again, we don't count the coefficient there, we just look, hey, we've got one substance making 2 or more substances, more than one. That's decomposition. Our next type of reaction is called either a single replacement, a single displacement, or sometimes people will leave off the single and they'll just call them replacement reactions or displacement reactions. So what are those? When you have a single switch of partners. And what do I mean by partners? I mean, there's a metal usually that's attached to some non-metal, either over common ions or just an element from the periodic table. It reacts, and that common ion switches from one metal to the other metal. So an example of that would be as if we had zinc, solid zinc with copper 2 sulfate, and we reacted those. What you actually end up with is zinc 2 sulfate. Or remember, with zinc, we don't have to say the 2 because zinc only forms the 2, so we can just call it zinc sulfate, and solid copper. So we see that this sulfate group used to be attached to copper, but then at the end it's attached to zinc. And so he switched partners, but only one thing is switched partners. Just the sulfates moved around, everything else is the same, and we call that a single replacement reaction. So if there's a single replacement, what do you guess there also is? You betcha, a double replacement. Or a double displacement. You can use either term. We're going to use replacement in this class as our primary term, but displacement is actually a more common term. So what do we have? We have two partner switch. This is what I think of like the country line dancing, country square dancing. Double replacement reaction. We've got lead to nitrate, aqueous, plus sodium iodide, aqueous, forming lead to iodide solid plus sodium nitrate aqueous, and it looks something like that. And I forgot a 2 over here as well. So what do we have? We have lead coupled with nitrate. That nitrate switches places, and at the end, he's coupled with the sodium. We've got sodium coupled to iodide, but at the end, that iodide is now coupled to our lead, so it's switched place. So both the nitrate and the iodide have switched places. Two things switching places is called a double replacement reaction. One more for this page is what we call a combustion reaction. And a combustion reaction, there's actually different definitions depending on who you talk to. Some chemists will actually call any reaction with oxygen a combustion reaction. We're going to narrow it down a little bit more. We're going to say it's a reaction, RXN is short for reaction, with oxygen to form CO2 and water. So all three of those things have to be present for it to be a combustion reaction for the purposes of our class. Reaction with oxygen, forming CO2, and forming water. If one of those is missing, it's not a combustion reaction. So an example is anytime we burn something. So we're going to say C2H6, ethane, react it with oxygen, and we're going to form two CO2s and H2O. Do we have a balanced reaction here? We've got 2 carbons on the left, 2 carbons on the right, 6 hydrogens on the left, but only 2 on the right. So we got to put a 3 there. So now we've got 6 hydrogens on the left, 6 hydrogens on the right. But what do we have? We have 2 oxygens on the left, and we've got 2 times 2 is 4 plus 3. 4, 5, 6, 7 oxygens. How do we balance 7 when we've got O2? I'm okay with balancing a 7 over 2. Some people will say you can never have a fractional coefficient, in which case we'd have to multiply the whole thing by 2, and we get a 2 in front of C2H6, a 7 in front of oxygen, a 4 in front of CO2, and a 6 in front of water. But I'm okay with the fractional one when you're putting a fractional one on one of the molecular diatomics. I'm okay with that. All right, so there is our combustion reaction. We're reacting with oxygen to form CO2 and water. So those are 1, 2, 3, 4, 5 different types of reactions. Combination, 2 things become 1 thing. Decomposition, 1 thing becomes 2 or more things. Replacement, 1 partner switches. Double replacement, 2 partners switch. And combustion, burning things to make CO2 and water. There's one more classification of reaction we're going to talk about in this class that's a little more complicated, so it gets its own page. And they're called oxidation reduction reactions. Extraordinarily important in biological systems. Lots and lots of redox reactions take place in biological systems. And that word I just used, redox, is just a shorthand we use for oxidation reduction reactions, because saying oxidation reduction reactions over and over again takes a long time. So, oxidation reduction reactions, what are they? The redox reactions, remember RXN is short for reaction, are when electrons change hands. how do we know if electrons change hands? Well, what happens to something when it loses an electron? If you lose that negative charge, you become a little more positive. What happens to something when it gains electrons? If you're gaining those negative things in your life, you get a little more negative. And so what we have to look at in this is what happens to the charges as we progress in our reaction. So we're going to do an example. We're going to do an example of zinc and copper 2 plus goes to zinc 2 plus and copper. And we want to know, is this a redox reaction? Is this a reaction where electrons change hands? And how we're going to do that is we're going to look at the charge of our metals. It's almost always the metals. At least in this class, it's always the metals. We're going to look at the charges of those metals and see what they are before the reaction and after the reaction, right? Before the reaction arrow and after the reaction arrow. Let's start over here with zinc solid, right? It's just a big pile of zinc. You've got this little cube here. That's a big pile of zinc. What's the charge on a big pile of zinc? Like, I don't know. Why would I know that? Well, if we think about it, can there be a charge on a big pile of zinc? In order to be a charge, what do you need to do? You need to give away electrons. Well, did I give anything for the zinc to give electrons to? No. Or you take electrons. Where is it going to get those electrons from? So it turns out elements all by themselves in what we call their standard states have no charge. And so this zinc has a charge of 0. What about at the end, after the reaction? It says Zn2 plus there. Well, that 2 plus tells me that I got a +2 on the zinc. And you're like, well, Professor Clemens, didn't you just tell me that an element all by itself doesn't have a charge? Yes, I did. But here, we're specifically saying that the zinc has a +2. In order to have a +2 somewhere around, there's probably a couple negative ions running around that we didn't write in this reaction. Could be nitrate, could be other things. We don't write them in the reaction just to simplify things, but they are around. So if you see something that says Zn2 plus, you can assume that the zinc has a +2 charge. So what happened? My zinc went from 0 to +2. How do you go from a charge of 0 to +2? Do you gain electrons or lose electrons? Right. We lost 2 electrons. And if you lose 2 electrons, you change your charge. And we know now that electrons are moving around in this reaction, and so we can call this a redox reaction. And specifically, here the zinc going from a charge of 0 to +2, it is losing electrons, and loss of electrons is what we call oxidation. Okay, sorry about the background sounds there. It's oxidation. The oxidation is loss of electrons. So we say here that the zinc underwent oxidation, or the zinc was oxidized. So what do you think happens to the copper? If the zinc lost 2 electrons, those electrons just didn't go out in the middle of nowhere, did it? So what do you think happened to the copper? Chances are the copper gained those 2 electrons. So let's look at the charges on the copper. Here, this +2, or the 2 plus, tells me that my copper must have a +2 charge. Here we've got copper all by itself, no charge listed, nobody else to be paired with, and so it must have a charge of 0. And so my copper went from +2 to 0. How do you go from +2 down to 0? You've got to gain electrons. In fact, 2 electrons. And we call this reduction. Why do we call it reduction? Because we're actually reducing its charge. We're reducing the charge down from +2 to 0. And that's why we call it reduction. It's a little weird because when you add electrons, you call it reduction, but that's what we do. A mnemonic that people use for this is oil rig. Oil rig. Oxidation is loss of electrons. Rig, reduction, is gain of electrons. Okay. So that is oxidation reduction reactions. What you need to be able to do is identify oxidation reduction reactions by looking at whether any charges changed hands. And you also need to be able to identify what was oxidized and what was reduced. Now, in some cases, it's a little more difficult. So in that example we had on the last page of our zinc solid plus copper sulfate, copper 2 sulfate goes to zinc 2 sulfate plus copper solid. How do we know if there's any charges in here? Well, some things are easy. We see zinc all by itself. We know that's a 0. We see copper all by itself. We know that's a 0. So we can start there. But what about in that right here? How do we figure out whether there's a charge? And we actually go back to what we learned about naming compounds. How do we know what the charge is on that copper? We know because we've memorized or can look up that the charge on the sulfate is a -2. And nature loves balance, so the copper must have a charge of +2 to balance it out. Same thing over here on the zinc sulfate. Here, this has a -2, and so there must be a +2 over here to balance it out. And we now know that our copper is a +2, and our zinc is a +2. So we can look at individual ones. What did the zinc do? The zinc went from 0 to +2, and if you go from 0 to +2, you lost electrons. We call that oxidation. What do we know happened to the copper? It went from from +2 down to 0, and we call that reduction. So we were able to identify an oxidation-reduction reaction, and also who was oxidized and who was reduced, by using some of our knowledge about ionic compounds, that they always balance out in their charge. And we used that information from when we learned how to name things. So those are our classifications of reactions. The hardest one is oxidation-reduction reaction, but again, we're mostly just looking at our metals. What's the charges on our metals, and how do they change as the reaction happens? There are classes of oxidation-reduction reactions that don't talk about metals, but we're not going to talk about those too much in this class. All right, our next topic. Why do reactions even happen? What makes it so that when you add baking soda and vinegar, it goes and makes that lovely little volcano of bubbles? Why doesn't everything do that? Or why doesn't nothing do that? What is the thing that drives chemical reactions? And it turns out one of the primary drivers of chemical reactions is energy. Now, we're going to talk about it on a very simple level. It's a little more complicated than what we're going to talk about. But for the most part, if you think about what's going to make you happier, if you're in a high-stress situation, or if you're kind of relaxed on the beach, just watching the waves come in, where would you rather be? You'd probably be at the beach, just kind of relaxing, sipping a soda or whatever it is you like to sip. And it's a much lower energy state. You're like, oh, I'm calm. I'm relaxed, okay? And so we might do that when we're talking about our own personal state. We might say, hey, I want to be as relaxed as possible. And it turns out reactions want to do the same thing. They want to be as relaxed as possible as well. And so one of the things that drives reactions is their ability to lower energy. What do I mean by lower energy? What we're going to do is we're going to draw a chart here where energy is going up on this axis. And this part here we're going to call the reaction progress. What do we mean by reaction progress? I mean, if we start over here and draw a line here, this is our reactants. It's where we start. So as we go out on the left-hand side of this chart, it's where we start. As we head over towards the right, we get closer and closer to our products. Now, most reactions in the world that happen because the products are lower in energy than the reactants. And so it's kind of a happy thing, right? You run, reactants are kind of high energy, and then the products are relaxed and a little happier. And it's tempting. We can just draw maybe a little line connecting these two, and you'll see people do that. And we just say, hey, the reactants roll down over to the products. And in fact, people often use the marble analogy. It says, hey, if I just push this little marble down, it'll roll all the way by itself down to products, and that's how we know the reaction happens. But it turns out it's slightly more complicated than that, because I know if I take natural gas, right, I turn on the stove, it'll burn. However, if I don't put a little spark in there, I can just turn on that gas and let it go all I want, and it won't burn. Right? Have you ever not lit it, and for whatever reason it took a long time to burn, and then finally it lit one, right? So there was a time when it wasn't burning because you didn't put in that spark yet. Okay? So in order to get the reaction started, it turns out we have to get over what's called an activation barrier. And so I'm going to use my little Lego guy here. He wants to get from one side of his reaction to the other side of the reaction. And if there wasn't this barrier here, right, he could just walk across. In fact, even if we tilt it down, right, he could just walk down, and he'd be happier down here, lower energy than when he started. But if we put this barrier in the way, and he's trying to walk down, he can't really do that very well, can he? Because there's this barrier in the way. He's actually got to get up and over the barrier. Now, as soon as he gets over the barrier, it's really easy to fall down the other side of that barrier. But he's got to get up that barrier first. And it turns out all reactions have a little barrier that make it difficult for the reaction to start. Some are big, and the reaction happens very slowly. Some are very small, and the reaction happens very quickly. So in our reaction of baking soda and vinegar, that reacts almost immediately. So what would you guess? Is the barrier very big, or is the barrier very small? Yeah, you're right. The barrier must be very small. How we draw that barrier is we draw a little barrier. We draw a little hump that says there's a little bit of energy we need to put in first to get my little guy over that barrier before he can fall down to where he wants to be. And we call that barrier the energy from the top there to the bottom there, to the reactants, to where we start. We call that EA, or the activation energy. It's the energy it takes to get a reaction started. So until I put that reaction activation energy into my natural gas, nothing happens. It just sits there and combines with oxygen, or mixes with the oxygen, but doesn't react with it. But once I get that reaction going, then it keeps going. So that activation energy is really important. If you know that one of the slogans for diamonds is "a diamond is forever," but it turns out that diamonds are unstable. All diamonds in the world, once you take them out of the ground, spontaneously convert into graphite, the stuff you find in a pencil. So do people really worry when they're wearing little diamond rings that it's going to turn to a pencil lead over time? They don't. Why? Because although it's unstable, although it will happen, that reaction barrier is enormous, and it takes a really long time for anybody to get over that reaction barrier. And so you don't really worry about it. So it turns out, a diamond is about 400,000 years is kind of what you're talking, but it's not a very catchy slogan, and so people didn't use it. So those are our most common types of reactions where our products are lower in energy. This energy that we have in between the reactants and the products is how much energy the reaction gives off. So when we burn our methane, our natural gas, and oxygen, it gives off a lot of heat. And that heat comes from this part right here, the energy difference between the reactants and the products. These are what we call exothermic reactions. And if you remember, exo means outside. And it means the heat is given out into the world. So a reaction that's exothermic, like burning methane and oxygen, is going to give out heat to the world, because if I have less energy at the end, the energy's got to go somewhere, and it goes away as heat. But it turns out there's other reactions that are the opposite. And there's other reactions where if we draw this same set of axes here, energy on the left, reaction progress on the bottom, there's reactions that start off at a lower energy and go up to a higher energy. And if you think of the marble analogy, it's pretty hard to get that reaction started, right? You've got to roll way uphill in order to get that reaction started. So that reaction's not going to happen all by itself. And you're right, for the most part, it doesn't. But there actually are a few times where it does. and you've probably had some experience with it. No, I've never had experience with that. Well, what reaction do you know, right? An exothermic reaction is one that gives off heat. Here, in order to have my products have more energy at the end than they did at the beginning as reactants, I've got to put in energy. So I've got to suck energy out from the world around me, which is going to make the world cold. So what reaction do you know that spontaneously gets cold? And probably you've used one of those instant ice packs. You break it up, there's some chemicals inside there that mix, and as they mix, the temperature goes down, and you feel cold. Remember, cold doesn't actually exist. It's just the loss of heat. What you're feeling is the loss of heat. So heat's being absorbed by that reaction, and we feel cold. There's still this activation barrier, activation energy. Right? It's always from where we start, our reactants, up to the peak there. That's how much energy it takes to get started. Once I get the marble up here, it'll roll spontaneously down. This is called an endothermic reaction. It's one that absorbs heat. And we feel it as cold because it's absorbing heat from us or from the surrounding area. Not as common because the products are higher in energy. There's not very many of them that are spontaneous. You're going to find many, many more exothermic reactions that are spontaneous, but the other kind also exists. So those are two things we use to talk about the energy of reactions. And for the most part, what things we're trying to do is this exothermic type of thing is lower their energy. There's a reason these other ones still exist, but again, it's kind of complicated. You want to get into kind of second semester general chemistry to be able to talk about that one. So we've got this reaction here. What do we want to do if we want to speed it up or slow it down? How do we make a reaction go faster? There's this reaction that's really good, does some really cool stuff. How do we make it go faster and do that cool stuff even more? Or there's this reaction that we don't want to happen. We don't want this thing to rust or decay. How can we make sure that it doesn't do that? Well, it turns out there's three primary ways that we affect the rate of reactions, whether they go fast or whether they go slow. And they are temperature, concentration, and catalysts. And we're going to talk about each of those individually. Temperature. If you remember, temperature is a measure of kinetic energy. Which means that if something's cold, it's moving kind of slowly, as you got some cold atoms and molecules moving around. But what are they doing? They're not bumping into each other very much. They're not bumping into the walls very much or anything like that because they're moving fairly slowly. However, if we take those two same things and start increasing the temperature, what I find is that they're moving around very, very quickly. They're hitting the walls a lot more. They're hitting each other a lot more. More things can happen. Right? If you're hitting each other more often, right, and a reaction requires two things to hit each other, right? We're not going to react from over here. Hey, you over there, you want to react with me? Sure. No, you actually have to hit each other. You have to get close to each other to react. But if you're really fast and you're bumped around, you're going to do that a lot more. And so temperature, one of the ways we can speed up a reaction is by speeding up the temperature. Now, what that also does is if we go back to our Lego model here of our reaction barrier, and we've got this little Lego guy, and he's trying to get over this barrier, right? It's a very large barrier. If he kind of saunters up to the barrier and says, oh, I'm going to go over the barrier, right? He's not really going to go over that barrier. But if you start increasing his temperature, he comes back from way over here, and he does a running sprint, and he might have enough energy to get over that barrier because he's got more energy, right? He's going faster. He can jump higher. You're not going to kind of just go and be able to get over that barrier very easily. So temperature, measure of kinetic energy, the faster you're going, the more often you bump into people, and also the higher your chances of having enough energy to get over that little barrier that you want to get over. The next one, concentration. What is concentration? Concentration is a measure of number in a given space. Okay. Measure of number in a given space. So a high concentration means you have a lot in a given space. A low concentration means you have a very small number in a given space. I'm going to make my barrier a little bit smaller here for this demonstration. And I do only have one Lego guy, so we're going to have to pretend. But right, if one Lego guy is sitting there and he's just kind of walking around, right, he hits the barrier every once in a while, but not much happens. But there's a small chance that he's not careful and he falls over that little barrier and goes to the other side. But that's when there's one of them. But what if you had 1,000 people crowded around here and they're all kind of crowded and they're all bumping this barrier? What's the chance that someone's going to fall over that barrier? It's a lot higher just because there's more people around doing those things. The other thing, remember, is in order to react, things have to collide. If I've got a lot of people around, there's a lot more people for him to collide with, a lot more people for him to react with. And so that increases his chances of reacting and makes our reaction go even faster. So if we increase temperature, we speed people up and we make them more likely to hit each other and more likely to have enough energy to go over the barrier. If we increase concentration, there's just more people for him to be able to bounce off of. And there's also more chance, just because there's more people trying to get over the barrier, that someone's going to get over that barrier. Our last one is a catalyst. Okay, so what is a catalyst? Now, a catalyst is something that speeds up a reaction. How does it speed up the reaction? Well, it turns out what it doesn't do is what we've already talked about. It doesn't try to get this guy over that barrier in a more efficient way. What it does is it says, well, you know what? I'm just going to look at my barrier here and be like, well, instead of trying to go over, let me put my barrier back together here. Instead of trying to go over this barrier here that looks really, really daunting, he's going to say, well, is there another way I can get over there? And he kind of walks around and finds that there's another path that gets him to the same spot, which has a much smaller barrier. And he's able to just kind of walk up to that, hop over it, and get over onto the other side. And it's very easy for him to do because this barrier is much smaller than the other barrier that I was talking about. And that's what a catalyst does. It doesn't actually change anything about the reaction. You still have the same reactants and you have the same products. You get to the same spot, but it takes a different route that has a lower activation energy. So a catalyst, instead of taking the route that looks like that, it'll find a different route that looks like that. Same reactants, same products, but a much smaller activation energy there that makes it easy for it to get over. Now, which one of these is the best? Well, temperature makes a pretty big effect. For every 10 degrees Celsius, you tend to double the speed of a reaction. Concentration can make a big effect too, but a well-done catalyst does amazing things. You want to know how amazing? Let's think about our eyeballs. It turns out everything you've ever seen in your entire life comes from one molecule called retinal. And what retinal does is when it comes in, it's in a certain shape. And I'm going to do it like, let's see, like this. So it's in a certain shape like this. And when light comes in, it makes the molecule rotate just like that. And all it does is change its shape. Now, what your brain does is it interprets that change of shape as I just saw light. So it turns out everything you've ever seen is actually just a molecule changing from one shape to another shape. And your brain interprets that as I've seen something. It's crazy. Now, if anybody's out there as a gamer, you might know approximately how fast we see, because what do you want in a game? You want a refresh rate of at least 30 hertz or higher so that the game looks very, very smooth, because that's about what we see. We see about 30 times per second. And if we see about 30 times per second, that must mean that these little molecules that start off like this and then flip over, in order for us to see again, they've got to flip back over so the next thing of light can come in and make them flip over again. So they're flipping like this constantly. And they've got to do that, and it turns out to see about 30 times per second, they've got to be doing that in about 1/100th of a second or so, is flipping back over. So here's what you do as an experiment. Instead of having those molecules in the back of our eyeball doing that, you take that molecule and you just stick it in a beaker. Bing! We stick it in a beaker down here. We put some light in, we make it flip, and then we watch. How long does it take this molecule to flip back all on its own? In our body, like I said, it takes about 1/100th of a second, 1/100 seconds, 0.01 seconds. So we did that, we put it in a beaker, we stick it there and we watch it and we wait. And we wait. And we wait. And then we die. Because in order for most of the molecules to switch back, it takes about 400 years. If the molecule is all by itself. 400 years? No, I can't. Yeah, it's crazy. It takes about 400 years for that molecule to switch back all on its own. But in our body, it does it in 1/100th of a second. That is a major speed up. How does it do it? There's a catalyst. There's a catalyst in the back of our eyeballs whose only job is to take that molecule from here back to here so that we can see again. Now, in the body, we call a catalyst an enzyme. And its only job is to speed up very specific types of reactions. And how it does it is by giving it a different path. Instead of having to go over this giant barrier here, it goes over a different path. And you can think about that in a mountain analogy too, right? Two ways of getting over a mountain. One is to go way over the mountain. That's going to take you a lot of time and a lot of energy. And the other is like, let me just walk around the mountain. And then that's going to be a much easier thing to do. I still get to the other side of the mountain. I still get to my products, but I did it maybe faster and certainly easier. So those are the three ways we affect reactions: temperatures, concentration, and catalysts, which in the body we call enzymes. Thanks.